So now I'm going to explain about Additive NTT, and this is used in BNews because BNews wants to use Reed-Solomon code because it achieves maximum distance. So for MDS, because it's a linear encoding and it uses a matrix vector multiplication, and the Van der Monde matrix is MDS matrix, maximum distance separable matrix, but BNews is a snark deck using a characteristic to finite field. Here, characteristic stands what it means is if you add any same two elements, it gives 0. So basically, BNews addition is XOR. So if you add same elements twice, it's 0. So, and every F2 to the R finite fields are characteristic 2 if you look in the Wikipedia. But they are challenged. If you use radix to FFT using this characteristic finite fields, we can use naive way, or we can use radix to FFT. And I'm gonna tell in the background section. And to overcome this limitation, this paper is original name is novel polynomial basis, and this novel polynomial basis is compared to monomial basis. It uses a completely different basis, and I'm gonna tell you what this means in the background too. And so characteristic finite field is in this form, and monomial basis, like if you construct polynomial with coefficient, the basis will be like 1x, x squared, or x2 to the d minus 1, something like that. But it uses completely du1, and it achieves like n log n complexity for both space and computational time. And so let me first begin with how we represent polynomial in coefficient form using an existing monomial basis. If you use monomial basis, we can create a polynomial in such a way, and as we all know, we can create a polynomial using a different basis called Lagrange basis. That we can create a polynomial in an evaluation form like this. And in radix to FFT, we use a Lagrange basis using a roots of unity. So if you also look for like Lagrange polynomial in Wikipedia, then they use a different notation for these two terms. Is generally it can be represented as like x subscript j, x subscript I, but because we are using a radix to NTT, we use the radix to FFT, we use roots of unity, but because we compute this over finite fields, that's why we should call technically radix to NTT, but for simplicity, we keep saying it as a FFT. And to convert to coefficient form the polynomial to polynomial in evaluation form, we need to use this matrix, and this matrix is called Van der Monde matrix, and this is the MDS. And because we are using a roots of unity, this roots of unity has this property. If you divide if you run this process, this has these two factor, and by definition, nth roots of unity shouldn't have a 1 in a only omega 0 or omega n should have 1, and other elements shouldn't have 1. What this means? Then it means omega 2 n over 2 is minus 1. Using this property, we can create a Cooley-Turkey algorithm. So polynomial P can be divided in even parts and odd parts, and we can change polynomial into this form. And if we substitute x with minus x, which means x times omega to n over 2, that we have this one. That what? Oh,
What if n is odd? But it's radix 2.
yes, yes. So what this means? So what we evaluated is p over omega 0 to omega n minus 1, and now the problem is changed to the half-sized problem like PE and PO, but two half-sized problem. That's the key core part. How does FFT achieve n log n? And to show and to compare how delta is in radix to FFT and additive NTT, I define delta, and this delta will be appeared in the later too. And if we define delta x in this way, and as you can see here, the polynomial can be reduced in a recursive way. The problem of the compute evaluations over some domain will be changed to this in this process, using this process. So by recursively applying this process, the computational complexity will become n log n. So 4 times, like, so one huge problem becomes like 2 times log 2 sized problem, 4 times log 4 sized problem. Half n over 4. Yeah, and IFFT computes in an inverse way. So if we have an inverse matrix of the van der Waals matrix, we can switch it back to evaluation form to coefficient form, and this also can be achieved in n log n. So radix to FFT, if you use this way, then what we need is monomial basis. If you use monomial basis, we can compute FFT or IFFT in a fast way. But here the problem is, in order to use FFT, we need a large size to audacity. What this means is this only works for the prime field, which is form of 2 to the s times t plus 1, so that 2 to the kth roots of unity can be determined as follows. So by definition, or by lemma of Fermat's last theorem, Fermat's little theorem, G, which is co-prime to the P, G to the P minus 1 will be 1 mod P, and by definition P is 2 to the s times t plus 1, so P minus 1 will become 2 to the s times t, and the objective of this is to get the 2 to the kth roots of unity. So we remain 2 to the k part here, and the rest of part will be put inside the parentheses when we get this, and this the value inside the parentheses will become roots of unity. And what this means, except for 0, then the field becomes the multiplicative subgroup, and f the multiplicative subgroup fp x will have the order of 2 to the s times t, and this has a large, if the order of the multiplicative subgroup has a large 2 to the s, then we can use FFT effectively. But yeah, and this kind of field we call like FFT friendly fields, but the field is form of characteristic to finite fields. This has this form, f2 to the r, and if you compute the order of the multiplicative subgroup, this gives us 2 to the r minus 1, and this doesn't have a two-orderity at all. So the question is, if the characteristic to finite field, you want to use the FFT, then what can we do with this field? And if we use different mechanism like how radix to FFT does, then we need a different. I'm not sure this is a natural question, but yeah. So in order to overcome this limitation, they create a different basis, and yeah. Actually, this is a motivation why they do, like, you invent new polynomial bases, and why the characteristic to finite field can be used with radix to FFT. So if I keep moving on, now the omega is not a root of unity anymore, and delta will be new defined. I added delta in the background section to compare with easily, or to understand easily what it means, but yeah, this will be defined newly. So now, before defining polynomial basis, let me first define omega I, and you can interpret. So any elements of f2 to the r will be correspond to some omega I, and I basically some index, and I subscript k, you can think of as the value that is used in bit representation. And so you can think of like 0 in f2 to the r will be omega 0, 1 in f2 to the r will be omega 1, or something like that. And each omega I can be also composed of some basis vector, which is v0 to vi minus 1. Using this bit representation ik, we can express omega I in this form. So you can think of it as like v something will be the new polynomial basis. You can interpret it in this way. So, but in the later section, v will not appear, but omega will appear later. So if I keep continuing, so now we're going to define something called subspace vanishing polynomial, which is big W jx, which is a product of x plus omega I, and I will be iterated from 0 to 2 to the j minus 1. So I give you some examples. So W0x will be x plus omega 0, and W1x will be x plus omega 0, x plus omega 1, and W2x will be x plus omega 0, x plus omega 1, x plus omega 2, x plus omega 3. And as you can see, the degree of each polynomial will be 2 to the j. And the roots of, for example, W2x will be omega 0, omega 1, omega 2, omega 3. The reason why these four are roots is because f2 to the r has characteristic 2 features, which means, in other words, if you add same elements twice, it will be 0. So if you evaluate W2x at point omega 0, this will be 0 or something like that. And there's a lemma. So all this lemma is taken from the paper, so numbering is match it. And wjx is an f2 linearized polynomial, and the lemma 1 is actually pointing to this. So if you flatten omega z x plus y, if you draw this polynomial in your head, that this will be separated wjx plus omega z y, because it has the same degree, and the coefficient will be the coefficients belong to the same degree will be added, so this will be hold. So now it's time to define a new polynomial basis, which is xix and xix will be defined with the polynomial we defined previously, the subspace vanishing polynomial. And this will be something like this. And it's so complicated when you take a first look at this. So you just imagine that this will be new x, like so. We if you use monomial base, the polynomial will be defined like c0 plus c1x, c2x squared, something like that. Now we're gonna define polynomial with like c0 x0x, which is 1, c1 x1x, c2 x2x, so, and blah blah blah. And this new polynomial basis will evaluate it something like this. So if you flatten this, so x0x, because all the bit representation will be 0, so this will be 1. x1x will be like only the r is 2 to the r part, so only the 0 one part is enabled, and the rest of parts will be, the rest part of ij will be 0, right? So all these will be 1 except for double 0 part. So x1x will be this by using the definition of subspace linear polynomial. x2x, only the second part, if you interpret it as a like little endian, then the second part, or w1, only be activated, and the rest of the bit will be 0. So w1 is enabled, and this will become like x plus omega 0, x plus omega 1 over omega 2 plus omega 0 times omega 2 plus omega 1. So yeah, this is the example from the first 5 example of the new polynomial basis. And
so xi is same as vi.
What is vi? Yes, correct. Yeah. So the coefficient form of some n-1 degree, because the degree of xix will be I, so n-1 degree invariant polynomial, the degree that the polynomial can have at maximum, at most 2 to the r-1, because of it is divided by x2 to the 2 to the r. So and they use this some notation, something like this bracket with dn. So I just use the same notation. So this is the new polynomial with the polynomial. Sometimes it says novel polynomial basis or polynomial basis instead of monomial basis. And then the evaluation form, this polynomial will have something like L part with omega 0. And if you imagine if you imagine like coset or RS encoding part, omega L will be the part that control the coset or the RS encoding. So basically RS encoding will be blown up like by lambda a row inverse part, right? So what they do is they first run this I inverse FFT first, and then they call this process row inverse times by controlling different W omega L.
This is like kind of going back, but I was kind of curious for the basis diagram, like the new polynomial basis diagram.
Is this
One above.
one of this one?
Yeah.
Yeah.
So, x x2 and x4 cleanly divide and have a clear pattern, but why does x3 have like x plus? Wait.
Oh, sorry. No, you.
I have to think about it. I'll get back to you on that. Sorry, I'm trying to figure out how this works. Oh, why are there no like for x3 I was expecting it to be the bottom part being like root omega 3 plus omega 0 and then omega 3 plus omega 1 then omega 3 plus omega 2, but it's a different formula.
It's like in big representation. So it's like omega 2 is like 2 to 2.
Okay.
So like x3 is 2 to 1 plus 2 to 0, right? That's why it's omega 0 and omega 1.
Okay.
And x2 is like 2 to the 1, so it's just omega 1. Do you see the pattern?
No.
But I have a typo here. This should be one.
Yeah.
So omega 3 is made from, sorry, x3 is made from omega, x3 is made from x1 times x2, right?
Oh,
X3 is x1 times x2.
Yeah.
Not. Yeah, kinda. You can say that.
Yeah, numerator part is actually multiplication.
Because the bit representation is like that.
Why is it not, you can say that, why is it you can say that and not like,
Because the denominator part is different.
but like, if you look at
Oh.
the equation for it.
Yeah, same. Sorry, same.
So x3 is
Yeah,
x1
yes,
x2.
you're correct.
Okay. Then why is it, wait, then why is x4 something like w2 over w2?
It's because of the bit representation.
God, what?
But if you like, I think you can just multiply x3. No, actually not. So omega. So it's like 2 to the 2, right? 4 is.
Okay.
So like omega 2 stands for that bit, like the third bit, third list to the significant bit.
Okay.
And omega 0 is the least significant bit,
Yeah.
omega 1 is like that, so x3 is like 0th bit plus 1th, the next bit.
Oh, plus the third. So 3 bits from the significant.
No, 3 is like the 0th, the last bit, and the 2 bits should be 1, right?
The second bit should be 1?
The second and
The first bit.
second and first bit should be 1, right? To make it 3.
Okay, yeah.
So that's why it's omega 0 and omega 1.
I see.
X4 is only 1 bit, right?
Yeah.
It's the third least significant bit should be 1,
Yeah.
so that's why it's like that.
Okay, I see.
Oh, I can edit. This one, right? Yeah.
Why did it move? Could you explain to me what the small L is
What? Very
for
small.
the evaluation form?
This is used when you create a code set, but code set is not appeared in the paper, but it's used in RS encoding. So RS encoding is you need to increase the masses by a factor of row inverse, right?
Oh, okay, yeah.
So if you don't have omega L, then there's no way to increase your message size. And omega L is the way to increase your message size by choosing a different L. So every time you invoke FFT, then you get the same size message, same size evaluations, and you should run this process for like row inverse times.
Okay.
Then you get the RS encoding.
Okay. So it's just a factor to allow for increase in message width?
Yes.
Okay.
Yeah, this is the only place that is used. Otherwise, it doesn't have to be there. Okay, then if I'm moving on, so delta, now we're going to define delta, and this is looks very ugly, but yeah, but you need to remember this form because it will be used frequently in the below. This will look like this, and if you if, for example n is 8, the delta will have only this part, so basically, so let me briefly explain or compute with you. So if I start with, so n will be like, because n is 8, if I 3, then it's delta 3m will become dm, which is this up to d0 to d7. So delta 3 0x will be d0, delta 3 1x will be d1, and delta 3 7x will be d7. And so then I only can have like 0 1 2, right? Because n is 8, I only can have like 0 1 2, and and if, as I define in m here, m only can be ranged between 0 to 2 to the I. So if I is 2, then m only can have 0 to 3, and 0 1 and 0 0, something like that. So these will be the values that this delta function can have on when n is 8. And if I, for example, like how d8x will be recursively computed, and this is an example, and let's see one by one. And so we define this polynomial with the polynomial basis, right? Xix. So I flatten this with the sublinear vanishing polynomials like this. And if, as we did in FFT, if first we combine the even part with some bit reverser, and then 0, 4 will be matched, and 2 and 6 will be matched, and then 1 and 5 will match, then 3 and 7 will be combined, and they have some common part like this. 2, 6, 3 and 7 have a common part, which is W1 x over W1 of omega 2, and this part, this old part, also have a common part, W0 x over W0 omega 1. And by definition, if you see above, so this is D0, right? D0, and this is D4. This part will become like this. Because you just add D2mx is D3mx and something, and D3 something, right? But D3 is delta 3 something is D something. I stop this screen at moment for certain period to convince yourself. Which line is unclear?
I'm just trying to do it in my head and I can't do it properly. Like for example, for the delta 02 x, the first term.
Delta 02, oh yeah, this one, yeah.
I'm trying to calculate like D4.
Yeah, because I is here 2, right?
Yeah.
Then I plus 1 becomes 3, right?
Yeah.
Delta 3m, and as I said before here, delta 3m will be dm. So this, the first part here, D3, delta 3, 0x, right? Which is D0.
Yeah.
So here D0.
Okay, it's D4.
D4, here delta 3, 4, right?
Yeah.
Delta 3, 4 is D4. Yeah, using the same technique, all these 4 will become delta 2 something.
Okay.
And the rest of parts just using the above path above. This only will be used just one time, and the rest of part just use this path. Then there's an additional lemma 2. Can I move on? Lemma 2, and if you see delta I, this will be used a lot of times in below. Delta im x plus y, and if y is one of omega 2, omega, so omega b, which b from 0 to 2 to the I minus 1, then delta I, yeah, this is used this. So this will hold. So
is y can be basically anything, any element.
yes, if it belongs to this range.
Okay.
So it should be bigger than 2 to the I. So basically here, if you see where here L
Mm-hmm.
should be bigger than 2 to the n.
Mm-hmm. Otherwise, it will
Yeah,
make
yeah,
sense.
it doesn't make sense. So I will show you how it's varied. So if I is log to n, both of them are dm, so it's same. If I is log to n minus 1, then by definition, this is the top part of this, and by definition this will become dm because this is right. This will be this, and yes, this will become. I should remove this second line. This and this are same. I need to delete later. And using lemma 1, I said subspace linear Vanish polynomial can be divided in this way. Lemma 1. And since the y, if y is this, is a Vanish polynomial, and all these are roots of this.
All what? All.
So this is a vanishing polynomial,
Okay.
and those are the roots of this polynomial.
Ah, right. I see.
Yes, that's why this holds. And inductively, if c plus 1 is hold, then this also come from the above part of the definition of delta function. Using lemma 1, WC x plus y will be linearly divided like this, and also because these are roots of WC polynomial, this becomes 0. So I should notate it. No. So this will be, I missed something. So the denominator part will be omega c x plus WC x plus WC y, right? Then y is 0. That's why this become this, and I missed something. So this also hold. So this, so no, I think I need to refine this part. This is not clear.
Which part?
So this should be reinforced, so that the what I want to show this is hold, but this will be the denominator part of this fraction, and WC of x plus y becomes WC of x plus WC of y, but WC of y is 0, so it will become WC of x of WC of omega 2 to the c, but it doesn't tell us that delta mc x plus y is equal to it doesn't tell us this. We need to do something more to make this part into this. I think ChatGPT misses something.
I also want to ask, for the above case, so case 2.
Yes.
Yeah, it says like y exists, or the roots of unity for y are as such. Like
This
y
one.
is-
Yes.
So that means that I equals log 2 n minus 1, right?
Yes.
Okay. Why? Okay. Okay. So it would just be equals 0 to, what is it? Oh my god. N, to 0 to n roots of unity.
There's no such roots of unity in this polynomial basis, but yeah, kind of is a roots of this polynomial.
Okay. And then there would be n plus 1 roots? N minus 1? N minus 1 roots?
This if w is I,
Okay.
Wix has a 2 to the I solutions.
Okay. And then when we substitute I as log 2n minus 1, it's n minus 1.
So for example, n is 8,
Yeah.
then I is 2,
Mm-hmm.
so W2x has four solutions.
Okay. Okay.
I think if this part is very simple. If I write something more, so please review in the document level. This is not that hard. Anyway, so now the transform FFT. Uh, yeah, now the FFT maps psi appears. This will be the notation that we use for FFT, and almost similarly this. So I give you example, like so this transform will compute if n is 8, 3k L2, and k will be like this much. If it, you can think of this like this is a coefficient. Maybe I need to add what is k, but yeah, basically we are given with these coefficients, and we're gonna compute 0, 0, L, which will become this evaluation form. So if you replace, so for example, like so if n is 8, I 3. So if I 3, maybe m also have a definition above, but I need to copy the definition m again. But basically m is the number between 0 to 0 and 2 to the I. So when I3, then m can have like 0 to 7, and in this case will be the coefficient. If I0, then this will have like b times 1, right? And 2 to the I is 1, so it can have like just n elements, which is 0 to n minus 1. I also stop the screen for some moment to get used to this notation. Uh, can I go above? Because can I go above, or because it doesn't connect to whether this is equal to d something. So if you remember, so what we need to compute is I need to replace p to d n bracket But basically we need to dn evaluation at point this, right? And I need to highlight that dA evaluation something is equal to delta 0, 0. I forgot to highlight. So if you remember this and take a look at this again, then this is it's actually FFT.
I can see the first line, but the second line. So is I see.
In this case, the second line of the formula,
Yes.
you can just substitute omega n minus 1 for omega 7, right?
Ah, yes, yes.
Oh. If phi is 0, right, in the size definition.
Here?
Yeah.
Yeah.
So let's say I is 0.
Yes.
Oh, I over 2i is just n minus 1.
Yes.
Okay, I see.
Because p times 1, and this will be b 0 to n minus 1.
Yeah.
Mm.
Yes.
It's very complex. Notation is not, friendly. So if I keep going, I just show you the formulas and I show you the example below. But so basically, psi I comma l comma l can be divided in these two subsets. So delta im double c plus double l and delta im double c plus double l plus w, sorry, omega 2 to the I with a half sized. I think we can take a look at this and we can go back to here again. So so I prepare two layers because delta has a two path, like when I is log to n and I is between 0 to log to n minus 1. So I prepare for 2, and this will use the down part in the below. So that psi 2 comma l comma l, by definition it will compute these two, and by definition of delta it will become this. And because here I is log to n, this will become dm plus 4, dm plus 4. Then psi 2 comma l comma l can be split into this and this, and this is exactly the, if I go above a little bit, this psi is no, I should say this will have subset of this and this. we can compute this using this and this. Here the values computed differently, but the value that is composed is same. Sorry, this and this and this are same value. Oh no, this and this are same value, right? This and this are same value. Yeah, so
exactly same.
no, I mean this part, delta part.
Ah.
Delta part is same. So what I mean by is
dm plus
yeah. So what I want to convince you is this part is this and this will be divided into this and this part, which is one is delta 3m omega 0 and delta 3m omega 4 plus omega l is missing, but and I didn't show you why it can be computed psi, so you can just forget about psi right now. But I want to convince you that this one will be divided into these two parts or delta parts. And if I go down a little bit, one layer below, if n is 8, I is 1, then this will split it into this and this. I want to convince you. And psi 1ml by definition, it will have this. And by definition of delta, is long. It's flattened in this way. It's just I just flattened delta with the definition. And here I use some trick because it doesn't give us any proof in the paper, just I guess to make this sense. So here what I used is, so omega 2 is this one, right? Each element represents the element in the f2 to the r, right? What I use is omega k. If I plus j is equal to k, then I can flatten this with I and j. So I flatten omega 2 with omega 0 plus omega 2. And if you go here, I also flatten 2 to omega 0 and omega 2. And if you go here, I flatten omega 6 to omega 4 to omega 4 and omega 6.
How does the flattening work?
Flattening? I use this fact. So each omega I is an element of the f2 to the r. If f2 omega 0 represents 0 in f2 to the r, and 2 represents omega 2 represents 2 in f2 to the r, then summation of f omega 0 and omega 2 will be omega 2, right? Otherwise it doesn't satisfy the group structure. And omega 6 we should have like omega 2 plus omega 4.
I think it is easier if you see the
Yeah.
in that form.
Yeah.
So IK is just the bit representation of the I. So omega 2 plus omega 4
Yeah.
is gonna be like bit representation and bit representation added on top of it, and then VK, right? Do you get what I'm saying?
Yes.
So are you saying omega 2 plus omega 4 equals omega 6?
Yes.
Yes.
Okay.
Yes.
So it's like adding the bit representation on top. So if you see, it's gonna be like bit representation of omega 2 added on top of bit representation of omega 4, right? You see?
Okay, so it's just automatically, okay.
Yeah, so it's gonna be just omega 6, same as.
Yes. That's for her.
So for example, if you add like omega 3 and omega 1, then it's gonna be omega 2.
What did you add?
Is it gonna? I think it's gonna be like that, no?
What did you add?
Omega 3 plus omega 1.
Omega 4.
Because omega 3, so it's gonna carry? Is it gonna carry here? Because I thought IK is just in the
Ah.
F2? Or maybe it's not in F2. Is it? It should be, right? It's in base representation, so IK should be.
Yeah, maybe if the carries.
I think, actually, maybe it will carry, yes.
Yeah, if it doesn't hold, if it doesn't have carry property, then the group structure is broken.
So you're saying V1 plus V1 is gonna be V2?
Yes.
Then it's not a basis, no? Basis, each vector, the basis should be orthogonal.
Yes, you're right. Yes, you're right. But otherwise, this breaks the group property.
Yeah, then, yeah, I mean, which breaks? You mean V1 plus V1?
So omega, so I assume that omega, set of omega I is an additional representation of the F2 to the R, maybe
right.
field or group. So so 1 plus 2 should be 3 in F2 to the R, right?
So we're replying V1 plus V1 is V2.
No. V1 plus V1 should be 0 because it's characteristic 2. Yeah, then you're right. You're right, sorry.
I mean, there is something contradiction coming.
You're right.
So omega 1 is going to be just V1, right?
Yeah.
So V1 plus V1